So this one has an n value, or what my degree is on number 1 is 5. It has a degree of 5. Oh, I don't have a pen here. A degree of 5. And then if I have multiple things multiplied together that equals 0, one of those has to be 0. So x minus 6 equals 0, or x squared minus 4 equals 0, or x squared plus 9 equals 0. So this one, I'm going to add 4 to both sides. I'm just going to do this one. Subtract 9. So x squared equals 4, and x squared equals negative 9. Square root both of them. And x is going to equal 6 plus or minus 2 plus or minus 3i. Questions? Yeah, you told me that, by the way. And I probably am not recording. Oh, I am. Okay, I did good this time. And then for the second one, okay, I have a degree of, let's see, I have a degree of 3, 4, 5, 6, a degree of 6. So I've got 2x minus 3 equals 0, x squared plus 8 equals 0, and x cubed minus 8 equals 0. So if I subtract 8 and add 8, and I might as well add 3, and I get 2x equals 3, and x squared equals negative 8, and x cubed equals positive 8. Divided by 2, square root this one, cube root this one. X is going to equal 3/2. Plus or minus, let's see, 8 is 4 times 2. 2i root 2 and 2. Okay? Questions? Okay. So a lot of what we're doing today is kind of talking about graphs and talking about their functions. I mean, their characteristics. I'm so sorry. Talking about their characteristics. I'm going to try and make this look like this, and then I'll read it off the computer screen and shrink it down if I need to write on it. So, so the first thing we're going to talk about is shape and end behavior of a polynomial graph. So the graph of a polynomial function is smooth. It has no gaps, sharp corners, or cusps. So that means when I'm drawing it, which we may end up doing, I'm just not sure where we're going with it. Well, we're going to draw a couple of graphs. Leslie. And I don't remember who else I let in. We are going to draw a couple graphs. So when you are drawing them, they're smooth curves like this first one here. No sharp corners or like weird little things like this, like little bird looking things. So no sharp corners. They're always nice smooth curves. Attempt to draw nice smooth curves. Let's see. So then we have to talk about the degree of the polynomial. And the degree has a lot to do with what the shape looks like. And if it's an even degree with a positive leading coefficient, which means the coefficient is greater than 0. Okay? So if it's an even degree, I want you to kind of look at the graphs and see what they kind of all have in common and describe that in the chat box, please. So if it's an even degree, and it's a positive leading coefficient, or A is greater than 0, kind of tell me what you think they all have in common, please. Go ahead. Okay. So when you say they're in behavior, you have to actually tell me what you mean by their in behavior. Wow, okay. Nice, John. No, you're not wrong. So someone put in there are all positive. So when you're saying are all positive, I need to know what you mean by all positive. I'm sorry. I'm just not quite sure exactly what you're saying. Okay. Emma, you're making some great observations, by the way. Thank you for putting so many in there. Oh, Emma Mickelson, you're the only one. Emma M, you're the only one online right now. You guys can say stuff out loud, you know, instead of being on your phone.
I have to pick up my brother, so I'm trying to figure out who he is.
Who is this? I think that must be Abraham. Okay. I should put up your. Okay, so I think only one person actually kind of said what we're looking for. So let me talk about this, and it was about the in behavior. So the one thing they all have in common. By the way, I want to say this. Let's see. Let me go back up here. And where does it say? So they all have positive and negative slopes. Yes, that is true. But even if A was not greater than 0, they would all have positive and negative slopes. Okay, so that was great. And then the other one that was kind of a vague one, in behavior is infinite for both sides. So even if A was not greater than 0, the in behavior would be infinite for both sides. And they almost every single graph there is crosses the y-axis. And these all seem to make valleys, which, yeah, they all seem to make valleys. They all range in both positive and negative portions of the graph. Not all are straight lines. They weren't all yours, by the way. Okay, so if I look at this, I'm just going to kind of get the highlighter, I guess. If I look at this and this, what's happening? And this one and this one. Oh, by the way, pretend these all have arrows on the end, right? I guess she should have probably said that. Someone say in simple terms what's happening. I need to get this all on the iPad. In simple terms, what's happening at the end if A is greater than 0? Yes, y goes to positive infinity every single time in simple terms, right? So if I have an even degree, so I'm looking at my equation, and it's an even degree, so 2, 4, 6, 8, 10, right? Even degree. Then the ends of my graph are always going to point, and A is greater than 1, which means it's not negative, right? A is always going to be pointing, it's always going to open. It opens up, basically, right? You can say it opens The easiest way to say it is it opens up, right? These all open up. No matter what's happening in between, all the junk that's happening in between, no matter what, it still all opens up. It's the easiest way to say it. Opens up. Yay, it opens up. Okay? Y goes to positive infinity. You can say that, right? As x goes to negative infinity, y goes to positive infinity. Remember writing that last year? As x goes to negative infinity, y goes to positive infinity. That's describing the end behavior. We're going to get to describing it right now, but I mean, we're going to get to describing it later. But right now, just simple description. What's happening if A is greater than 0 or positive and I have an even degree, it opens up. So every time, okay? So if I go to the next page, now my leading coefficient is, let me make this bigger, is less than 0. What's in common now? What's happening this time? Yes. Yeah. So this is negative coefficient, right? I'm still even. They still open in the same direction, right? Only this time because my coefficient, because A, my coefficient, is negative, instead of opening up, it's going to open down. Okay? No matter what happens in between. So if I have an even degree, both my endpoints are going to open in the same direction. And it's either going to open up or it's going to open down. How do I tell if it opens up or down? Well, if the leading coefficient is positive or negative. If the leading coefficient is positive, it opens up. If the leading coefficient is negative, it opens down. Just like with a quadratic, everything is the same as that. So it doesn't matter if it's the fourth, the sixth, the eighth, whatever that degree is, it acts exactly the same as a quadratic. It just has a whole bunch of other stuff happening in between it. Stuff, did you like that? Has a lot of other stuff happening in there. Okay, so now we're going to go to an odd degree, and we're going to talk about that because we really haven't really dealt with odd degrees before. And maybe I can get the screen to move. There we go. Here we go. So if I have an odd degree, and I have a positive leading coefficient, which means it's greater than 0. What's happening? What do all the graphs have in common this time? It's a little harder to describe. So think about it. I'm going to just give a hint. So think about it. Last time we were talking about the ends, what was happening at the ends. So with the degrees, we're probably talking about what's happening at the ends of the graphs, right? So that's kind of what we're going to look at on this, not the stuff in between. How are you going to describe this pattern? Okay, so talk about your positive and negative endings and concentrate on that and describe that a little better in more detail. And let me read. Yeah, Hannah, that's great. Only on 3 of them is that true? Oh, I see what you're saying. Yeah. Yeah, Emma. So on this one, this is kind of how I look at this one. So if I have, right, here's, oops. So here's my ends, here's my end. What's happening to the graph? If I don't pay attention to all the stuff in between my endpoints, I'm not going to look at all the hills and valleys. I'm just going to look at my endpoints. And this is how I kind of look at it, right? What's happening between here and here, and here and here, and here and here, here and here, and here and here? What's happening? It always has a what? There you go. It has a positive slope, right? It starts low and goes high. Or ends high. Let's not say goes high, ends high. Ends high. So if I have an odd degree and it's positive, it's going to start low, go high. From left to right, starts low, ends high. Okay? Just in general terms, okay? And then, of course, if I go to the negative coefficient, same thing, odd degree, I have a negative coefficient, and I look at my endpoints only, and I don't pay attention to any of the things in between, because on this, I'm only looking at the behavior of the graph and what's happening. Oh, that was so not a straight line. Right? This time I have a negative slope. Overall, over the whole thing, I end up with a negative slope, right? I'm starting high. And ending low. Okay, does anybody have any questions about that? That is just off the degree. Look, I got all of that information for a graph just off the degree and the leading coefficient. One piece of the equation tells me all that information about what the graph looks like. Okay, so now you're going to answer this little question. Which of these graphs, here, let me make it bigger. Which of these graphs could be the graph of f of x equals negative 3x to the fourth power and y? A, B, C, or D? Yes, honey.
Why is it that, what's the difference between these ones? It says negative leading coefficients, the one that do the up and down,
Uh-huh.
and the other ones that do the negative slope?
So one's an even degree and one's an odd degree.
Where does it say that? Oh, up here. Okay.
So the ones that open in the same direction are an even degree, and the ones that open in opposite directions are an odd degree. Even? Odd. Nice, Daniel. Yes, Hannah. Good. Okay, so if I look at the equation has an even degree because it's 4, and then it's a negative leading coefficient. So even degree means both endpoints, and I should have written, sorry, even degree, both endpoints, same direction. So that leaves out that one and that one. And then odd, oh, not odd, negative leading coefficient means it opens down. So that means it's this one, okay? Any questions on that one? Do you understand why it can't be C? Because it opens in opposite directions. It doesn't open in the same direction. The endpoints are in opposite directions. Oh, okay, good. Okay. All right. So now we're going to talk about the number of turning points or bumps. At most, I can have n minus 1 turning points. And n is the degree of my function. Oh, come on. The degree of my polynomial function. So I can have n minus 1 turning points. So for a degree 2 or quadratic, right? For quadratic, I can have 1 turning point, 1 bump. That's it. Okay? I can only have 1 for degree 2. That gives me 2 x-intercepts, right? 2 x-intercepts. So I have 1 turning point. For degree 3, I can either have 2 turning points, right? 3 minus 1 gives me 2 turning points. Or, because it says at most, that means I can have less than that, right? I can also have 1 turning point. So, and we're going to talk about these flat points. I might as well. Says no points, no bumps, but 1 flex point. This point here, see how it kind of goes up and then it flattens out a little bit? That's because we've got some imaginary points in there. So I've got 1 x-intercept and then I have some imaginary points in there. So when I have some imaginary points in there, it kind of starts flattening out at that section. So when it starts going flat, that means I've got some more imaginary points in there. So this one will have 1 real and 2 imaginary x-intercepts. Okay? And then this one that has degree 3 that has 3 x-intercepts, look at that, 1, 2, 3, it has 3 x-intercepts, which means it has to have 2 bumps in it because it has to go through all 3 x-intercepts. So you'll have 2 bumps. Whew. And then we've got a degree 4. We've got 2 options for a degree 4. I can have 3 bumps, which would be 4 minus 1 is 3 bumps, because I've got 4 x-intercepts. And to make my graph fit through those 4 x-intercepts, it has to turn 3 times. 1, 2, 3. Okay, as you can see, if you look at the graph, it turns. It goes 1, 2, 3 to make it through those 4 x-intercepts. Well, sometimes it might only have 2 x-intercepts. Okay, because an degree 4 or an even degree will have usually at least 2, unless of course it's going up and doesn't touch the x-axis, right? But look again, it flattened out here. So it's got 2 x-intercepts, so 2 real intercepts and 2 imaginary. And the imaginary is where it's down here flat, where my graph starts going more flat. So 2 real is where it crosses the x-axis. 2 imaginary is where it flattens out. And then this one has 4 x-intercepts because it's degree 4, so it should have 4 x-intercepts. And the turning points always have something to do with the x-intercepts. And that's why I'm talking about that, even though they show the bumps on here. So let's talk about degree 5. By the way, degree 5 and 6 are probably the most you'll ever get for us to graph. We probably won't do more than that, unless it's already factored for you. We're not going to make you factor it yourselves. I won't say in college they won't make you factor it for yourself, but we're not going to make you factor it for yourself here. Okay, degree 5, again, in this case has one x-intercept. So this has one real intercept and 4 imaginary. Because it flattens out. Notice the difference between, I want to kind of look at the difference between the 5 and the 3. Degree 3 kind of has a little flatness here. Look at degree 5. The bigger the degree, the flatter it goes before the curve starts going up. So if it's degree 7, which we don't have on here, that flat portion would be wider. Degree 9, it would be wider. 11, it would be wider. So that flatter portion just keeps getting wider and wider and wider if we only have one real intercept, okay? So for the second one, I've got 2, basically, because there's one here, right? 2 real intercepts and 3 imaginary, and they've got that right there, okay? And then what do we have here? Ooh, degree 4 bumps. So we've got one here, one here, one here. And notice that these 2 right here, this one, I'm going to draw them in right here, the little arrows, do not flatten out. They're just kind of quick touches on the x-intercept. We haven't talked about that yet. We should have, I think that we're talking about that next. That means I have a multiple there. So think about when we had, how do I want to say that? Think about when we had like x minus 1 squared, right? That's x minus 1 times x minus 1. Well, I have x equals 1. Well, I have that 2 times, right? So when I'm graphing that, it becomes a touch or a kiss. It just touches or kisses the x-axis. So it just touches it and comes back down. So that means this is 2 here. There's 2 real here, 2 real here, and 1 real there where it crosses. So that's a total of 5. And we're going to talk about the touch versus the kiss in just a minute. The cross versus the touch in a minute. But that's how that one works. If it just goes up and touches it and doesn't go flat. And then degree 6, of course, 2 reals here, 4 imaginaries. Notice it's flatter than the 4th. Degree 6, here again, we've got 2 x-axis, and then it comes back up and is flat here again. So how do we find these turning points when we're graphing, which is what we're going to talk about tomorrow. Right now we're just talking about the characteristics, okay? So we're going to talk about finding these points. Usually we can find the x-intercepts. We can find the y-intercept. We can find a few other key points. We can find the x-intercept. We can find the y-intercepts. We can tell what's happening at the end. We can tell what's happening in behavior. We can tell which way it's opening, if I'm having a positive slope and negative slope, if they're opening in the same direction, opposite direction. And then for the little points in between, we kind of have to like say, let me take a point and just plug it into the equation, okay? Or sometimes we just sketch it. We're like, okay, these are where these points are. We're just going to kind of sketch it. We don't actually graph them. We sketch them. Difference in what we've taught you from before. Like before, it's always been they have to be exact. With polynomials and you're graphing them, it's usually never exact. We only want a few things exact: x-intercepts, y-intercepts, opening in the right direction, end in the right directions. Okay, and the rest is just approximately right. Okay, so we're going to get to that graphing. You guys are like, what? No, it doesn't have to be exact this time. Okay, so which equation could represent, oh, sorry, let me make this bigger. Which equation can represent, oh, that's a good way to spell graph. Okay, the graph below. Okay. Okay, well, those are all the same. Oh, I see that. Okay. So it's gotta be even. Okay. Oh. Come on, mouse. Fake spelling. Page 2. Page 3. Oh, it's Emma. It's okay, John. But yes, you're correct. And Hannah, that's correct also. Do you guys know? What did you say? Okay. 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 Okay, I get the point. Hi. Okay, so let's talk about this. So I know that they're opening in the same direction, right? So that means it has to be an even degree. So I'm going to check my degree first. And they're opening up, so that means it has to be a positive coefficient, right? So I can eliminate, I need to make this smaller, sorry, because my doesn't fit on my iPad. So I know that it can't be that one and it can't be that one because those are negative coefficients, right? Because it's opening up, so it has to be a positive coefficient. Are you okay with that? So that's going in just with what we learned from the first part, right? Okay, so then I know since they're both opening upwards instead of in opposite directions, it has to be an even degree. So this one is, let's see, 2, 3, 4, 5. This is a 5th degree. So I don't even have to use what I used before. I use what I learned from before. So I always start with what I know really well. And what I know really well is the degree, and right? So you might as well use that. I mean, this does have which somebody put in here. Let me see, what did they put? Because it has 3 bumps. It has 3 bumps, so they put B. Awesome. Okay, that is a perfectly reasonable answer. Awesome, it has 3 bumps. It could be B. Okay? Awesome. But that's not the way I thought about it. The first thing I went to, even degree. Let me see which one has an even. Well, it can't be D. And then I'm like, oh, it opens up. Can't be odd. I mean, sorry, can't be negative. Can't be odd. Can't be negative. So I crossed off those 2. Okay? Okay, so now we're going to talk about touch versus cross. And sorry, I used the word kiss. That's the way I learned it versus touch. I don't know. So you can laugh. It's okay. So I'll say kiss instead of touch a lot. So if you look at the 2 graphs or pictures, I guess it's a picture here that we have. Can you guys tell me, I'm not speaking Spanish back at you. I only know donde está el baño. So that's all. That's all I know. Which means if no one knows, where is the bathroom? All I know. Okay. After 3 years of Spanish, 30 some years ago, that's what I remember. Okay. Look at the graphs that's on there and the answers and tell me what the difference between a touch and a cross is. I know this is you guys observing, a lot of you observing today and coming up with the difference is. Emma, are you okay? Are you okay? Okay. It crosses. Oh, so just really quick, it's, remember the scale, sorry, I've got to think of how I want to say it. The scale on the x-axis is by fives, so nothing's going to be exactly on a, the scale's just by five. So think about, like on the first one here, I don't know if I should draw in here. So this first one, this should be 7. And this is 6, or -6, sorry. And this should be -6, and this should be 7, because it's by 5. So it's approximately it's still hitting at that number. I hope that helps a little bit. Does anybody have an idea? Anybody in here have an idea? You guys can talk, you know, they can hear you. Because I don't blend.
What the difference is?
Yeah.
One of them touches and one of them crosses.
So what's the difference?
One of them goes through the x-axis.
Yes, I understand, but how do you know when it does it?
Oh, you mean like in the equation?
Yeah.
I didn't know that.
Why not? They give the equation and they give everything in the picture. You didn't look at that part? He's like, one crosses and one touches. I understand that. But I want to know what the difference is.
It doesn't say look at the equation.
Oh, my Lanta.
It just says what's the difference.
Oh, my Lanta. Okay, now what's the difference in the equations? Yeah. Yeah, it has to do with the square. So which one is the square?
Touch.
Yeah, the touch. Right. So if I don't know how to say that actually. If it's a non-square, if it's just a factor by itself, a factor to the first power, there we go. If it's a factor to the first power, it will cross. So if it's a factor, oh, that is not a pin. A factor to the first power will cross the x-axis. A factor to the second power will touch, T-O-U-C-H, touch the x-axis. Okay, and then as the powers get bigger, so if it's a third, it will start flattening out, right? So it'll still cross, but it'll be flatter. If it's a fourth, it'll still touch it, but it'll be flatter. Okay, so the bigger the power, it's still, if it's an odd number, if it's an odd power, so if it's a factor to an odd power, it'll still cross. But it'll just be flatter. It'll start flattening out as it crosses through. If it's a even power, it'll still kiss it or touch it, but it'll just start flattening out, like in the last picture.
It's like to the 3, it'll be a longer kiss.
Yeah, no, it'll cross. Power of 3 will cross because it's odd.
But it will be
Odd numbers cross through,
right.
even powers kiss. So even, right here. So if that was a 4, it would do this. It would kind of come down and flatten out before it'd come back up.
Oh. So, okay, that makes sense.
Does that make sense?
So if it was a 4, then it would be like an extra long.
It would be a longer place. Yeah. And if it was a third, if this was a third, this would come up like this, and then it'd flatten out, and then it would go back up. It'd still cross, but it'd flatten out and go up across. So, yeah. Polynomial graphs are very interesting. And Desmos does graph them for you. Yes, which is very nice. Okay? Now we're going to go on. This kind of brings us to multiplicity. Multiplicity is the number of times. Oh, I'm sorry. I keep trying to make it so I can see it on my iPad, and I know it's smaller for you guys in class now. Multiplicity is the number of times a given factor appears in the factored form of the equation of a polynomial is called the multiplicity. The 0 associated with this factor, x equals 2, has a multiplicity of 2 because factor x minus 2 occurs twice. That's just an example that they came up with. So if I'm in my equation, I'm going to write an equation kind of to go with that. If I'm in my equation, it says y equals x minus 2 squared times x plus 3, right? How I would write my answer, my x-intercept answer, x would equal 2 multiplicity of 2 and then negative 3. So if I have a squared, now I'm going to show the multiplicity also. So it has a multiplicity of 2. So if my equation happened to be like I don't have any place to write on here. If my multiplicity happened to be this, like if I had y equals x plus 2 cubed x minus 5 to the 4th power x plus 3. Let's just say there, okay? Just made that up off the top of my head, right? And I'm going to solve for x, right? We all know it's the opposite of what's in the parentheses. You guys already know that, right? So x would equal negative 2 multiplicity of, that is not, and it's not a exponent. It's actually multiplicity of 3. And then 5 multiplicity of 4. And then negative 3. And why do we show the multiplicity? If we were not graphing them, we wouldn't need to show the multiplicity. But because we're graphing and we're starting to graph, I need to know, at 2, it's going to cross because it's a multiplicity of 3, and it's going to flatten out. And at 5, it's gonna kiss, but it's going to be flattened out because it's a multiplicity of 4. So I need to know that information when I'm graphing it. Does that make sense? So I need to know what the multiplicity is when I'm graphing it. Okay? Because that shows me where my flat spots are. And it also tells me if it kisses or if it touches. Kisses or crosses. Okay? You guys are like, no, why are we doing this? Okay, and this graph kind of talks about it. I mean, these boxes, multiplicity of 1, right? It just crosses each one. Even multiplicity, I'm not going to read them to you. I'm so sorry. There goes my voice. The graph touches, right? It just touches right here. It didn't flatten out. It just touches and goes through. Odd multiplicity, it flattens out and goes through right here. It crosses right there. So if it has an odd multiplicity, it will it'll still go through, it just flattens out. If it has an even multiplicity, it'll touch or kiss it and go back down in the same direction. All this stuff just to graph, right? So much easier to graph a quadratic. So the maximum number of x-intercepts is the degree, right? The maximum number of x-intercepts I can have is the degree of the polynomial. Can I have less than the degree of the polynomial? Yes, because I can have imaginary answers. Not all of my x-intercepts will be real. So the max number I can have is my degree. So if I have a degree 3, I can have 3 x-intercepts. But I may only have 1 real intercept and then 2 imaginary intercepts. So you might not get, you may not get the whole, all of the degree, all of the x, oh my Lanta, all of the x-intercepts of the same number as the degree. And we know that when we're talking about a quadratic, because remember a quadratic can have 0 x-intercepts, 2 x-intercepts, or 1 x-intercept, right? Depending on where it's placed at. So we know that it's possible not to have that degree 2 with 2 x-intercepts. So it can have imaginary x-intercepts. Okay, so even multiplicity, what does an even multiplicity do? It kisses or touches, T-O-U-C, touches the x-axis. And an odd multiplicity crosses the x-axis. Okay? Odd always crosses, but it flattens out, right? So multiplicity means it's going to flatten out no matter what. Okay? Well, no, it doesn't mean, it just means it's going to cross. I'm so sorry. Odd multiplicity definitely means it's going to flatten out. Even multiplicity just means it's going to kiss it. So just depends on how many multiples I'm going to have, whether it flattens out or not. And that's the whole big problem. So I'm going to zoom this up here. And it says, what is the minimum possible degree? Oh, come on, just stop. What is the minimum possible degree of the polynomial function graph below? That one's not too bad. Yeah, Hannah, good. Remember, degree is linked to x-intercepts also. Show of hands, show of fingers, how many? Yeah. Do you have an answer? Okay, do you have an answer, Emma? Yeah, good. Show of fingers, looks like show of fingers. So Lucy and everyone else who has not answered in homeland there, all I'm doing is counting my x-intercepts. That's it on this one. So that's the minimum number I can have. So 1, 2, 3, 4, 5. And I'd be willing to bet it's only 5 because there's no flat spots, right? If there are some flat spots, it could be more, but right now it's the minimum number is 5. So that's all I know. It could have some imaginary ones that we don't know about, but it's got a minimum number of 5. Does that make sense? Yeah. Okay. So now on number 4, given that a polynomial is of degree 6, which of the following could be its graph? So there's more than one choice. I'm just going to tell you guys. So which of the following could be its graph? So go ahead, pick a graph. I'm going to pause this. I don't know why I haven't paused all period.